established the laws of logarithms, having established the definition of the logarithm, having looked at some logarithmic equations, let's look at some other equations that don't have a log in them, but we'll need to use logarithms to solve them. So to start with, we'll start with the most basic type, and then we'll build it up to some of the more complex types. So let's start with this equation here. So let's say I've got 11 to the power of 7 minus 2x, which is equal to 100. And we want to solve that equation, so obviously it means I need to find the value of x. Now, to solve this equation, I need to use logarithms. Why? So remember we said that a to the power of x is equal to b is the same as log base a of b is equal to x. Those two statements are equivalent and are interchangeable, which means that I can rewrite this in terms of logarithms. Why I'd want to do that will become immediately obvious when I write it. So if I turn this from this form into logarithmic form, this becomes log base 11 of 100 is equal to 7 minus 2x. Now at this point, resist working that out on the calculator. Obviously, you can type that into the calculator, but it's going to give you a decimal, and we still then have to solve to get x. So just leave it like that, leave it in exact form, and rearrange that to get x to be the subject. So 2x would swap with this, so that would become 7, subtract this value, not too worried what that is right now, and then divide by 2. So actually, an exact solution to this problem would be 7 subtract log base 11 of 100 divided by 2. That's an exact solution. But if the exam wanted you to find it to 3DP, 4SF, something like that, you then type that into your calculator and you come out with a solution to a sufficient amount of accuracy as determined by the question. So to 3SF, that would be 2.54. Okay, so if we move on to this example is slightly different to the previous example, and it doesn't allow us to use the definition of a logarithm, because in order to turn to the definition of the logarithm, you need a numerical base to a variable equals to a number. Number, x, number. Here we've got a number to a variable, so 3 to the power of 2x minus 1, equals to another term of that form. That's not the form. A to the x equals b is not the same as a to the x is equal to b to the x, for example. So there is a powerful technique used when you have equations like this, where you have single terms, one on each side. We're going to see later what we do if you have more terms like that, which wouldn't allow you to use this. But if you've got a power term on one side, another power term on the other side, you can log both sides. A very powerful technique. So let me show you what I mean. If you've got terms like this, you can take the log of any base you like on both sides, as long as it's the same base. So what I'll do is I'll just write log. So I'll log the left-hand side, and I'll log the right-hand side. Now, you can take any base you like. As a mathematical convention, when you see log written without the base, the assumption it's base 10, and there's a special calculator button that would allow you to use that button. It prevents you from having to type in the base yourself, which saves a bit of time. Right, but if you want to do log base 2, log base 7, that's also fine. So if I've got log of 3 to the 2x minus 1 equals log to the 5 of 2 minus 7x, let's think, why did I do that? Well, think, what does that now allow me to do? If I've got a log here, let's think, the log laws. What does this now allow me to do? Have a look at this. Take a step to think. Why did I log it? Okay, I had to log on both sides. That's what I do to one side, I have to do to the other side. What does that now allow me to do? Well, log of base to a power allows me to bring down the power. Remember, that's really the problem here. That x is the unknown. It's stuck up as a power. and we can't use the definition, so it's sort of stuck up there and I can't do anything with it. But if you bring it down, okay, then it gives us more options. So let's bring down the whole of this power. So bring down the whole of 2x minus 1, and we'll do the same over here. Use a bracket because there's two terms in that power. So we end up with 2x minus 1 multiplied by log base 10 of 3. And if you want to write base 10 there you can, but log without a base is really just base 10. Then we have 2 minus 7x multiplied by log 5. Now, when you get that line there, it sort of throws people off sometimes, but remember log 3 and log 5 are numbers. If you've got a bracket, 2x minus 1 times a number equals another linear bracket times a number, it's a linear equation. So we have to just isolate the x terms on one side and the numbers on the other side. Refrain from using your calculator at this point. Try and get the x terms together on one side. So, where do the x terms appear? Look, x is over there. So I've got 2 log 3 lots of x from there, and there's x there, and I've got minus 7 log 5 lots of x on that side. So let's bring that across. So how many x's do I have? I've got 2 log 3 on the left-hand side, and I've got minus 7 log 5. If you bring it over, it will become plus 7 log 5. Now what about the number terms? The terms independent of x, you want to ship them across to the other side. Look, I've got minus log 3 here, that's not an x term, so let's take that across. That becomes positive log 3. And over here I've got 2 log 5. That's already on the side I want it. So I'll add that to 2 log 5. And finally, x would be all of this divided by that. If you want that in exact form, that would be your answer. Log 3 plus 2 log 5 divided by 2 log 3 plus 7 log 5. And that's 0.321 to 3 significant figures. What you need to remember is that if you've got an equation with two terms that are exponential terms, similar to this, if you log both sides, it gives you options from which you can work with. So let's try a slightly different example that applies the same sort of techniques, but doesn't look exactly like this. And let's see what you can make of the next one. It will involve a slightly different approach at the beginning. Okay, something slightly different comes out of it. But let's see what you attempt, and when we'll go through it. Okay, so let's try this one. 5 to the power of 1 minus x is 8 divided by 3 to the power of 5x. Right, so again, think about the techniques we've learned, have a go, and then I will provide a fully worked solution for this problem. This question like this would be 4 marks, so fair bit to do. So give it your best shot and we will go through it. So similar to what we said before, I've got two terms, one on each side, they're exponential terms. I can't use the direct definition of the log, but I can log both sides. Now, what you have to be careful about here is you cannot combine these terms. 8 doesn't have a power of 5x, 3 does. This does not become 8 over 3 to the power of 5x. What we could do is we could leave it as it is, we could log both sides, and then it's a division, so we could use the subtraction law. I think it makes it just slightly neater and presentable to bring this term up. You don't need to. There is a way of doing this, leaving it as it is, but I think let's just bring this up. So it becomes 5 to the power of 1 minus x multiplied by 3 to the power of 5x is equal to 8. Now, let's log both sides. Again, it doesn't matter which base you are going to use to log both sides. If you use a base of 5 or 3, it would make it slightly neater in the long run. But this question, which was asked, wanted this actually to 3SF. So because we want it to 3SF, it doesn't really matter which base you choose. So let's just stick to log base 10. So let's log base 10. Remember, log base 10, you don't need to write the base. So let's log this. And then you log the right-hand side. So at this point here, you need to take care with this, because you need to think what's going to happen. That power cannot come down at this stage. Stop the video, pause, think why. Why can't I bring down 1 minus x? You are going to be successful with logarithms if you are very confident in when and how to use the logarithm laws. You have to use them when they apply. So, we've had time to think. Hopefully we realised I could only bring down the 1 minus x if that wasn't there. Well, it is there. So what am I going to do about it? Well, this is a product. Look, it's a product. If you're logging a product, we have a rule that takes care of that. We need to separate these out, which we can. So we do log 5 to the power of 1 minus x plus log 3 to the power of 5x is equivalent to log 8. Remember, what we're using here is the fact that log of AB, log of any base of a product, is log of A plus log of B. We've learnt that in the logarithm laws. Now we can bring this power down because it fits the form of that third logarithm law. Same with 5x. So you have 1 minus x, that can now safely come down, plus 5x, I'm still going to use a bracket, log 8. Coming back to a previous comment I made, I said if you use log base 3 or 5, it would make it slightly nicer, and that's because if we use log base 5 instead of 10, log base 5 of 5 is, hopefully we realise, is 1. So that would just disappear, so it would make it nice. Now log base 5 of 3 wouldn't, so ultimately it would have got rid of one of those logs, which would have made it slightly nicer. Now we could have used log base 3 of 3 is also 1, so that would have disappeared, but we're still left with these two other logarithms, whichever way we go about it. So at this point here we've got a linear equation again, right? We've got a bracket, a linear bracket times a number, another linear term times a number, and log 8. So again, see where the x terms appear. So you could multiply this all out, but I think it gets quite messy. I think it's more effective to see where the x terms appear. So, in terms of x terms, I'm going to take the x terms to the other side and bring the numerical terms to the left-hand side. You could do it either way. So if I want the number terms on the left-hand side, it means I want the terms independent of x. So where are the terms that are independent of x? 1 times log 5. Okay, that's a... Right, so that will stay on the left-hand side. So I'll have log 5 on the left-hand side. That's an x term, so that will go on the other side. That's an x term, that will go on the other side. I'm going to deal with that in a minute. Now log 8 is a numerical term independent of x. Let's bring that across. So that will be minus log 8. And now let's factorise and bring across all the x terms. So I've got, look, I can see here for x, I've got 5 log 3. If you bring that across, that would be minus 5 log 3. What about here? Minus, look, I've got minus x log 5. If you bring that across, that would be x log 5. I've taken x out, so that's just plus log 5. And finally, to get x, you take this, and you divide by all of that. And this is the point you can use your calculator. Notice I'm using the calculator at the end of the calculation. Don't be tempted to use it earlier. And to 3SF, that turns out to be 0.121. As an exercise, you could see what happens if you used a different log, a different base for the log. The answer to that question is you should get the same answer. Okay, you could also combine those to become log of 5/8, okay, making it nicer for you. But if you're just looking for the answer to 3SF, those things are nice things to do, but not absolutely essential.